Welcome back to ECE 320A. Your first homework assignment is due today. Your second homework assignment, I hope you've started on already. That would be nice if you have. That means I would have already made the assignment. It isn't yet posted, so stay tuned for that. Homework 2 is not due a week from today, but roughly a week and a half. In 2 weeks is our first exam. And it will cover that material on homeworks 1 and 2, which is really material from chapters 10 and chapter 11, single phase and three-phase power. That's the plan. That's why that red parenthesis chapter 11 is down on the bottom of our goals. Hopefully we will get started with three-phase power, an introduction, in today's class. I don't know that we will, but if we do not, you can spend the weekend reading up on chapter 11 material. Hopefully, homework number 2 will be assigned by then. That's the plan. Today what I want to do is pick up where we stopped last time, which we stopped right before this example. I wanted to just do an illustrative example of working with phasors or vectors. And really, it's somewhat like one of your homework problems in that you're given a few quantities, but maybe not everything, and you kind of have to work your way around the unknowns in order to solve the problem, if that makes any sense. Maybe it will as we get into that particular problem. We'll just briefly talk about maximum power transfer. In a sinusoidal steady state case, you want to assign your load impedance, if you have freedom to assign it, to be the complex conjugate of your source impedance or your Thevenin impedance. We'll talk a little bit about that, but in a power context, it really doesn't make sense to do that. You want to push as much power as you can to the load. You don't want to really lose half of your power in the source impedance as you would in the load. And that's what happens here when you match impedances by setting it equal to the complex conjugate. This makes more sense in a communications sense when you're maybe have an antenna and you want to match your antenna with the electronics. Then you want to match the impedances so that you get as much power into your system. Or if you're doing a sensor, you want to make sure that you're being efficient with the way that you receive or transmit information. We'll then look at a power factor correction example, which should lead us into the three-phase power material at the end of the class. That's the plan. Let's start with an example. We are picking up where you left off in 220 with sinusoidal steady state analysis. Now we are simply applying that in a power context. Even though we are talking about power, we have to deal with voltages and currents. And when we do deal with voltages and currents, we have to remember that we are not just doing DC quantities anymore. Now we have sinusoidal steady state conditions, and we simplify that by putting us into the frequency domain or the phasor domain to analyze these systems. And when we do that, we need to make sure that we treat both magnitude and angle when we're solving these KVL and KCL equations. Or another way of thinking of that is that these quantities, voltages and currents, they add vectorially. As a very basic system configuration, we could have something as straightforward as this two-load system or two impedance system. We have a source voltage V sub G that's written as a phasor. It's magnitude and angle, and the magnitude, you need to make sure you're talking RMS or maximum magnitude when you do the problems. We now have, let's say, this voltage V sub 1 and V sub 2, and I try to indicate that those are phasors by the overbar or the barred notation. What we may not know is this current is going back and forth, but we typically say, oh, okay, let's just assume that it's going in the, let's say, left to right direction in this particular diagram. But sinusoidal steady state, it's actually going back and forth, but we simply denote one direction. When it is positive, this is the direction that it's moving when it's positive. Similarly with V sub G, when we're on the positive side of that waveform, this is then the direction of the polarity consistent with that on our voltage source. If we simply write a KVL equation, those are still valid. It's just that we need to make sure that we have the phasors being used, meaning if we simply walk around that circuit as you traditionally do in a mesh equation in the direction that I've indicated with the highlight, we simply say, okay, we are going in the negative terminal of the V sub G the way we've sketched it. That's now minus V sub G bar plus V sub 1 bar plus V sub 2 bar, and those vectorially need to sum to 0. Or maybe you're used to seeing this as the source is then dropped across those two impedances, V1 plus V2, in the direction that we have indicated. What you want to think about or keep in mind is the following picture. Now we might have V1 going up at this particular angle. V2, if we connect these head to tail, would again be oriented relative to the horizontal line going off to the right, and V sub 2 then might go at a different angle than theta sub 1. This might be V sub 2. What we hopefully understand, since we're dealing with phasors, is the fact that V sub G is the vector sum of those. It's not the length of V1 plus the length of V2, which I hope you see is not equivalent to that particular line. That line is supposed to be well connected, but you can draw better than I. Hopefully you can see in this particular example that the length of V1 is not equal to the length of V1. Whoops, what am I saying? I wanted to say V sub G. I'm going to have to stretch again. And if you're looking at the lectures or the video lectures, I actually indicated what time I took the stretch exercise in the video, if you want to wake up while you're watching. Hopefully that's the case, that you feel comfortable with that concept, that Vg is not equal to the length of V sub G. The magnitude of that source voltage is not necessarily equal to the sum of the magnitudes of V1 and V2. Let's look at an example. With that same picture, let me give you, and this usually causes everyone to get a little anxious. It's a word problem. So throw out your middle school, high school anxiety attack that you get when we say a word problem. This is how you're going to get most of your problems anyway in the real world, is somebody's going to tell you what they want or what they think they want, and you're going to have to try to figure out what they do want. So here it is. Suppose that V sub 2 RMS, and maybe I should be more descriptive, and so I'll try to be in this particular expression or in this example. I'm really meaning the magnitude of V sub 2, since I didn't put the bar over it. That's a little bit hard to infer, maybe. So let's do this. Let's say that the magnitude of V sub 2 in RMS is 40 volts. Let's assume that we're told that Z sub 2 is absorbing 80 watts. And maybe somebody tells you, oh, you know what, Z2 is inductive. Suppose they also tell you the magnitude of the source voltage, and maybe that magnitude is 120 volts, and the real power supplied by the source is 100 watts. And maybe they tell you, oh, and I really think the total load is inductive in nature, and the current has an RMS value of 5, meaning that's its magnitude. I'm not telling you what phase relationship it is with respect to the voltage in this circuit. We're given all of this description for this picture. V sub G, we're given its amplitude. We're told the magnitude of I. We're told the real power of Z1. Is that true? No. No, we were told the magnitude of V sub 2. We were told how much real power it was absorbing. And we were told how much power the source is supplying. That's what we know in this particular example, this series circuit. What we want to find is V sub 1 bar. So that's our goal. What we want to do is find the phasor voltage for load 1. We're given little pieces of information, and now we need to figure out how we use that information to try to find V1. If we were told the phasor form of V sub G and the phasor form of V sub 2, that'd be pretty easy to find V1 as a phasor. We would just subtract V2 from V sub G. But we don't know all of that information. We need to figure out what we do know. We do know the magnitude of that current. And we also know a little bit about some powers. Now, what I'm going to do is I'm going to make an assumption. I'm going to assume the current phase, or the phase of the current, the angle of the current, I'm going to use that as my reference angle. So I'm going to let that be 0. Nobody's told me where to draw my time t equals 0 line, so that's going to force my time t equals 0 line, basically. I'm going to assume the phase current is used as the reference phase. Or, that is, or i.e., theta sub I is 0 degrees. So now I've assumed that angle, 5 at 0. I don't know this voltage. That's the one I'm trying to find. I do know something a little bit more about Z sub 2. I do know that V sub 2's magnitude is 40 volts. I do know that P sub 2 is 80 watts. But I don't know the angle of V sub 2. I don't know the angle of the source. And it might be nice to know that if I need to find V sub 1 as a phasor. Do I know Q sub 2? Or what do I know about Q sub 2? Anything? We know load 2 is inductive, don't we? What does that mean about Q sub 2? It's going to be positive. If we find it, it better be positive. So we don't know what this is, but we do know that it's bigger than 0. Okay, so the question is Q sub 2 always negative in a capacitive impedance? And in this course, yes, that's what we're going to live with. I mean, if you had negative capacitance, I mean, if I formulated the problem wrong, it could be different. And if I simply say, I don't know what this load is, and say, you need to find it, you might find that it comes out to be positive or negative. Then you could say, okay, this looks more like a capacitor, or it's positive, it looks like an inductor. But we will be using, inductors give us positive Q, capacitors give us negative Q. Pardon? Do we know the magnitude of V1? Pardon? Well, what we don't know, well, we do know KVL, but what we don't know is we can't conclude really anything about the magnitude of V1 because we know this doesn't work. So keep this picture in mind. This may be inaccurate for the problem, but in general, we could have a V1 going in one direction, V2 in another, and V total, or V sub G, being completely different in angle. And those lengths, if you now put V1 and V2 in line, hopefully it's clear that that sum is bigger than V sub G. So the way that V1 and V2 combine directionally will influence V sub G, the source. Is that okay? Meaning we're going to have to find another way to calculate V1 versus just comparing 120 and 40, but maybe it would be somewhat close. That kind of gives us a feel for what V1 might be. We sort of, I mean, if this was a DC circuit, so if you didn't know how to solve the problem, you might say, well, I don't know, let me just assume Z1 and Z2 are real. What would I get then? Then you could know that the I's and the V's are all in phase, and you could use that relationship. You could do KVL for DC, and now you say, okay, if things aren't really wacky, then maybe V1 is close to 80 volts. Does everybody understand what I'm getting at when I say that? But in this case, it may be a little off, maybe a little different. What can we compute? We know some magnitudes, and what can we do with magnitudes? Or, in this case, oh, and didn't I say something about the source? I didn't write that down. What's the power of the source? So if I have P's, I have a couple of P's, and I have a voltage, and I also know the magnitude of that current. I know the magnitude of this voltage and the magnitude of that current for this element. I also know the same thing for this element. The source element, I know its magnitude of current, and I know its magnitude of voltage. What does that give you, product-wise? And you also know the sign of theta sub g. The question or the comment was, you know the sign, and I'm meaning SIGN, this, I think, right? So we know the signs, SIGN of theta sub g and, let's say, theta sub 2. Since they're all referenced to 0 degrees for the current, now our voltage angle is going to be the same as our theta for that element, if that makes any sense. So now the point was, do we know the power of, I think, I'm paraphrasing, what do we know? If this is the supply, and we're supplying 100 watts, maybe I should label that, and one of the loads is receiving or absorbing, we were told, 80 watts, what do we know about Z1? It's going, that we can add, right? We can add these powers, P's and Q's. We can't add S's. We can add S's vectorially. But we can add all our P's, we can add all our Q's. In this case, the way that I'm going to approach it is actually using the P's and the product of voltage and current. Voltage and current gives us apparent power. And the magnitude of my S's, the apparent power. And if I have the apparent power and I divide that into the real power, what does that give me? PF, right? Power factor. So if you're texting tonight and you say PF, somebody will know you're talking about power factor, right? I don't know, that probably has some other meaning in a text. I don't text, really. But if I said PF, then my family better know that I'm talking about power factor. I'll try it tonight and see what kind of a response I get. Here's a solution, and you should be starting to understand that there are many, many ways of attacking this problem. Let me look at the power factor of the second load. That's the ratio of P2 over V2's magnitude and I2's magnitude, but that's I2's magnitude is the same as I sub S's magnitude. It's a series connection. This tells us that we have 80 divided by, what was V2, 40, and I2 was 5. Does everybody understand where those numbers are coming from? The current's magnitude is 5. That's the series current. We were given the voltage magnitude of 40. This is now the apparent power of load 2. and we had the real power, and the ratio of real to apparent is the power factor. This is now 80 divided by 200, or 40 divided by 100, or 40%, or 0.4. This is a power factor of 0.4, and this, if you remember, is now the cosine of theta sub 2, where theta sub 2 is theta v sub 2 minus theta I sub 2. But theta I sub 2 is theta I, which was 0. So I can just get away with calling this theta sub 2. Somebody have a calculator? The inverse cosine of 0.4. Oh, and what's the sign of this result? So you can get a little sloppy here. If this was actually a leading power factor, I would be okay if you now said minus whatever this inverse cosine is. Is that making sense? But in this case, we know it's an inductive load. We should have a positive angle. If we do the inverse cosine of 0.4, I believe I ended up with 66.4 degrees, and this is a positive angle. So I'll emphasize that by putting the plus sign in there. Because we were told we had an inductive load or behavior for load 2. Now we know the direction of that voltage. So we know its magnitude and angle. We've got a fair amount, and that information, real power and apparent power, we knew for load 2, we actually have it for the source, don't we? Where you were told the magnitude of the source, we know its real power that it's delivering or supplying, and that will then allow us to find the angle of the source, theta sub g, by the same approach. If we say power factor of the generator or the source, I guess that's what the G stands for. That's the P sub G divided by V sub G RMS and I sub G. And 120 times 5 is 600. 520s. If you had 520s in your pocket, that would be 100. So you know you have 100 plus 500, 600 downstairs, 100 upstairs. This is now 1/6, so that theta sub g is now the inverse cosine of 1/6, which is a pretty big angle, 80.4 degrees. And again, it's positive because of the inductive nature of the question. The question said it was inductive in nature, the total load. Meaning if we now tried to sketch this, we have our, and these angles aren't accurate obviously, this should have been 66 degrees, which is less than 45 the way I've sketched it, but you can use your imagination. This is 66.4 degrees, and the length of that was 40. Then we knew that we had V sub G going off at 80 degrees, and its length was 120. And now we need to find this V1, whose angle is that. So if we sketch these accurately with our protractor and ruler, we could actually graphically determine V1. Question? Oh, no. So the question was, do we know if this, and let me show you what I'm referring to here. I think this is what the question was. Is this a right angle? No. That's just an artifact of my poor sketch. Okay, so this is not necessarily a right angle. Wow, you can't even see what I was trying to highlight. That's not a right angle, necessarily. Questions? Now we can actually compute the answer that we needed. We know the magnitude and angle of the source and the second load. We can compute the magnitude and angle for the first load. We now have V sub g as V1 plus V sub 2, and we can write that in all of its glory with its different components. We can say that we have V sub g cosine theta sub g plus j V sub g sine theta sub g is equal to V1 at an angle of theta 1 plus V2 cosine theta 2 plus V2 sine theta 2. And we have all of that information other than V1 and theta 1. But now we have two equations in two unknowns in just that one equation, because we have the the real part and the imaginary part. We'll equate the real parts and we'll equate the imaginary parts, or we'll simply write this down as a polar form answer. Is everybody okay with what we have? Yes. Thank you. Just making sure you guys were awake. Yes. The question was, do you need a J in front of the V2 sine of theta sub 2? Yes, that was the imaginary component of my V2 voltage. Yes, thank you. Other questions or comments? Now if we plug numbers in, we have 120 cosine of 80.4 plus J120 sine 80.4 minus 40 cosine of 66.4 minus J40 sine 66.4, and all of that, when combined, will be V1 at an angle theta 1. And if you do that, you end up with 4 plus J 81.7, which is 81.8 at almost a 90-degree angle, and it's almost 80. Remember, we started saying maybe it needs to be about 80. Yes, our original thought was not too far off in this particular problem. And that angle is not too far from 90 degrees. Questions on that? And you should be able to see that these magnitudes, V1, which was 81.8, is not quite the magnitude of V sub g minus the magnitude of V1. It's pretty close in this example, but it's not quite the same. And in general, it's not the same. It might not even be close. Questions on that? To drive home the fact that it's not necessarily close, you can have the same, or you need to make sure that when you're dealing with currents, in the sinusoidal steady state context, you're dealing with phasors, and those phasors, you need to keep track of those vectorially. A simple picture here. What's KCL tell me? It's still valid, isn't it? We can write KCL, we just need to keep track of the vector or the phasor quantities. So I already tricked somebody. That's an S, not a G, but that's I sub S. The source current is equal to those going out of the node if we were writing KCL at this top node. Sum of the currents in equal to sum of the currents out. I sub S bar is equal to I1 bar plus I2 bar. And as an example, whoops, suppose that I sub S was 10. What's the angle? 0. If that's all I'm telling you, if I simply said, oh, well, the real part of the current is 10, I might not be telling you all the information. In this case, I'm saying I sub S bar is 10. That's all there is. There's no imaginary part. Then you could have I1, let's say, as 7.13 at an angle of minus 52.48 degrees. And I sub 2 being 8 at 45 degrees. And I'll leave it up to you, but you should be able to see that 10 is not the same as 15 in this case, but if you broke this out into its component parts, I1 and I2, the imaginary parts will cancel and you'll end up with the real parts giving you 10, and 10 will equal 10 if you did it vectorially. Question?
What was the criteria for when the magnitude, the magnitude equal to the actual power quantity involved? The criteria for that? Only in networks of a single type of element, like all resistors or all capacitors or all inductors?
So the question was, when do we end up with the magnitudes summing consistently? Meaning, we have 10 is equal to, let's say I1's magnitude was 2 and I2's magnitude was 8. When would that happen? Well, there are many different ways that that could happen. You could have a all DC network, I'm sorry, an all resistor network. That's when you're going to really have that magnitude sum, and that's probably the easiest way to think about it. If you had a all inductive circuit, as long as your source was purely imaginary, then you could have the same thing. And a capacitive circuit, if your source was delivering magnetizing VARs in that direction, you could have your magnitudes all the same also. But you have to have those sort of one type of systems, either all resistors, all inductors, and there your sources have to be consistent with the loads that you're giving them or attaching those to. Questions on that? Remember, we need to keep track of these as phasors or use their vector or treat KVL and KCL vectorially. Let's quickly talk about the maximum power transfer. concept. And now I think in 220 you've already talked about this. For DC loads and circuits. Now let's look at under sinusoidal steady state conditions. The result, the generic result, is you actually want to match the load impedance with the source impedance, and here by match it has a little special meaning because we're dealing with phasors or complex quantities. If you had the luxury of selecting your load impedance, then in order to get the maximum amount of power to that load for that given system, you would want to create that load to be the complex conjugate of the Thevenin impedance of your system or circuit. Meaning if your source was inductive, you would need a capacitive load to give you this Thevenin or this complex conjugate behavior between your load and your Thevenin source. As I had tried to mention earlier, this is useful in a few contexts. Let's say for communication purposes, if you have antennas or supplies, you now want to match the antenna with your circuit, useful for communication and, let's say, sensing systems or environments. But if you read the book in this section, you will see what the power conditions end up being, and you'll see that half of your power is consumed in the Thevenin impedance and half is in the load when you get this maximum power transfer. And if you're dealing with power, you don't want this generator side to be consuming half of the power that you're creating. So you want to try to keep your resistance or impedance on the source side of the terminals as small as possible so that you can push out as much power to the system or the loads as possible. And that's what I'm trying to say here. It is not really this concept of Z load equaling Z Thevenin complex conjugate. It is not really what you are looking for. And I'll say in moving large blocks of power. You do not want half of your power consumed on the source side of the terminals. And that's not really mentioned in the book, but the book does derive these relationships. It does show you why the load needs to be equal to the complex conjugate of the Thevenin impedance. And for those details, I would refer you to the textbook, section 10.6. Pictorially or figuratively or in a diagram, let's say this is your source. you've now collapsed everything to the left of your terminals in question, let's say A and B, into some equivalent impedance, Z Thevenin. And if you are at liberty to select Z sub L to satisfy maximum power transfer, you would pick Z sub L to equal the complex conjugate of the Thevenin impedance. Questions on that? If Z sub L is some load, some plant that we are trying to drive, and this is the power company to the left of those terminals A and B, we don't want a lot of loss in the Z Thevenin inside the plant or getting to the customer. We want to deliver as much useful power, and which power is useful? Real, or the average power. That's the useful power. That's the power that gets converted into maybe some other form. That's the energy that gets converted into some other form of energy. What we are concerned with, though, is this reactive power. And what we may want to do is try to minimize that so that we drive the power factor where? To 1, or at least closer to 1. And that's what I want to talk about now. Let's talk about power factor correction. Suppose we're given the following system. Load 1 is, let's say, P1 of 48 kilowatts. Its power factor is 0.6, and that's not all I need to give you, is it? You need to be told whether it's inductive or whether it's lagging or whether it's capacitive and leading. In this case, let's say that it's lagging. That's load 1. And load 2, let's say that the real power of load 2 is 24 kilowatts. It has a power factor of 0.96, and it's leading. And let's say that the generator side or the source side is, well, let me not even sure what I need to do. So I'm just going to give you the magnitude for now. Maybe it will be the angle that we need also. But this is now RMS. And let's say that this is a 60 hertz system. What we want to eventually do is actually hang a capacitor or a bank of something that creates a capacitive component near the load sides. So load 1 could be one plant, load 2 could be another, or it could be two pieces of a big plant. And now that plant maybe has a bunch of capacitor banks that they want to switch in and out so that the power company looking in here at these two leftmost terminals is seeing something that looks pretty real. It looks like a real load to it. Even though at the load, one of those is an inductive load and one's a capacitive load. We want to now try to find that capacitor, and what's the capacitor impedance look like? If I said, give me the formula for a capacitor's impedance when we're dealing with sinusoidal steady state, what's the formula? Z sub C, right? 1 over j omega c or minus j over omega c. It's 1 over j omega c is how I remember it. This would now be 1 over j omega c. We want to find what c do we need to make those, now it's 3 loads, look real to the leftmost terminals. Is that making sense? Now, we're going to need quite a few pieces in order to solve this. So I'm going to give you a quiz while I try to clear my throat on the first part. Find the complex power S1. We're going to need some of that, if not all of it. So let's find S1 as a quiz. And that shouldn't take you too long to find. All right, let's see what we have. I'm going to actually do it maybe a little differently, but you can sort of check your work. You don't need to add anything, but we are in a pretty, based on what we've already done earlier today, it should be clear that we have enough information to compute the apparent power from this information. We have the power factor and we have P1, where P1 is now the magnitude of S1 cosine theta 1. Or this is S1 power factor 1. So that now S1 is going to be P1 divided by PF1, 48K over 0.6, or 80 kVA for an apparent power. That would be the magnitude of your complex power. You maybe didn't calculate that particular quantity. Like I said, I'm going to be doing it a different way maybe than what you did it. We can also find S2, the apparent power for S2. That's P2 over PF2. This was 24K over 0.96. That's not going to be much bigger than 24K. That's 25 kVA. That's the apparent powers of the two loads. Once I have those, I can now find the reactive power. And the way that I'm going to do that is actually, now I do want to use the fact that P1 and Q1, or P2 and Q2, are at right angles. One's horizontal and one's vertical. Meaning now I just have to start sketching right triangles to find Q2. S1 is the magnitude of, or it's the hypotenuse associated with the power triangle for, really trying to get you to scratch your head on that one. Got too happy with my squares and just made a subscript 2 also. So S1, the magnitude, is the square root of P1 squared plus Q1 squared. We know S1's magnitude. We know P1. We can solve for Q1. And we were told the sign that Q1 needs to be. We said one was lagging, one was leading. So this will give us something that's maybe not determinable from just doing the square root of a value, but we can determine which root we want by using the lagging or leading. In this case, Q1 is now the square root of S1 squared minus P1 squared, or we now have 80 squared minus 48K squared, giving us 64 kilivars. This coming because of the lagging. And similarly, we have Q sub 2 is the square root of S sub 2's magnitude squared minus P sub 2 squared. If we took the positive square root, it would be 7, but we were told this is capacitive or leading. We'll give that then this negative sign. And now we know Q1 and Q2, and you could compute your S1 and S2 from those. So you should have obtained for S1 48K plus J64K for S1. That was your answer. Now, we can also find, with this particular circuit, we can find these currents. At least we can find their magnitudes given the information we have. We have the apparent powers for S1 and S2. We have now well, the voltage is the same across those, and we know the magnitude of that voltage, and we know the apparent powers of both of those. We can now get the apparent current flowing through, or the magnitude of our current in loads 1 and load 2. Those are in parallel. We know our complex power formula. What is S in general? VRMS, IRMS star. If I now simply take the magnitude of both sides, I have that relationship for apparent power, voltage, and current for given elements. And now I can find the magnitude of I1 is S1 divided by V1. S1 we computed to be 80K, and that dividing 80,000 by 500 leaves us with 160 amps. If we look at the second current magnitude, that's now the magnitude or the apparent power of the second load divided by the voltage across that, which is the same as the voltage across V1. This was 25K divided by 500, and this is now 50 amps. We now know the magnitude of the current going through those loads. 160 for the first, 50 for the second. What's the total load power? So I could write this many different ways. If I do it this way, I'm sort of meaning, oh, keep it separated into real and reactive pieces. If I say load powers, you can ask on an exam if it's not clear, do you want the total complex? And if it's still not clear, write down what you are giving me. I'm computing the total complex power of the loads, or I'm finding this power. In this case, I want P12, which is P1 plus P2. That was 48 plus 24, is that right? 72 kilowatts. The reactive piece, I don't even remember what Q1 was. I think Q2 was minus 7, wasn't it? Q1 was 64. So this is now 57 kilovars. 64 minus 7. What's the apparent power of the loads? That's just the magnitude of S12, and we know what S12 is. That's 72 plus J57, K. This is now the square root of P12 squared plus Q12 squared. Doing that ends up with 91.8 kVA. Now that we know that, we can compute the magnitude of the supply current. We know the voltage is 500, and we know the apparent power that's being supplied by the source or the load. That's what S12 gave us. This is now 184 amps. And you hopefully are seeing that 184, which is the magnitude of the source current, is not equal to the magnitudes of the two load currents, 50 and 160. I12's magnitude is not equal to I1 magnitude plus I2's magnitude. But now what's the power factor of the total loads? Do we have enough information? I'm looking now for PF12. What's one way of computing the power factor? Real over apparent. We have the apparent, that's the 91.8. That's the apparent power of the loads. What's the total real power of the loads? The sum of the P's, P1 plus P2, which was 72 kilowatts. So that information can be used to compute the power factor of the total load, the combined loads. We just knew the two pieces before. Now we can say that we have P12 over the apparent power S12. This was now 72K over 91.8K. Or this is now 0.784 lagging. Which we started with one load which had a higher real consumption, but it was pretty inductive. It was a power factor of 0.6. We had another load that was capacitive in nature, and now their combination is giving us a combined load appearance that looks inductive, and its power factor is 0.7, whatever we just computed, 0.78. But we would really like to bring that to 1, or at least close to 1. And that's our goal. We want to pick capital C, the capacitor, that will effectively get rid of that inductive piece that's now present in those two loads, load 1 and load 2. We want to select 1 over j omega c in what way? And by moving that power factor of 0.784 closer to 1, here's what's going to happen. We're actually going to reduce the current that the source is having to supply. And if you remember a day or two ago, somebody said, well, there's still that resistor in the transmission line. So there is loss in the transmission line, but we can reduce that loss in what way? We probably can't change the line itself, so the resistance is the resistance. But if we reduce the current going through that line, we reduce the power consumed in that transmission line. If we can reduce that current magnitude, which is now way up at 184, can we make that smaller, then we won't have to be losing as much in the transmission line. And the way that we're going to reduce that 184 is by introducing a capacitor near the loads so that that reactive power stays near the loads, and the source, all the source sees is something that looks real. So the power company is saying, oh, your power factor is very close to 1. Good job. Because you've now switched in enough capacitors to make your effective load look real. Let's see if we can do that. So now what we want to do is reduce the current from the source by correcting the power factor. We'll do that by introducing this capacitor. And the purpose of that capacitor is we are trying to eliminate Q sub 1, 2. And what was Q sub 1, 2? 57 kVars. 57 kilovars. Can we pick a capacitor? And what was that Q1, 2? It was positive. We want to get rid of it. We're going to introduce a negative Q to completely annihilate that 57. That's what we want to do with the C. And you just told me that the impedance of a capacitor is 1 over j omega c. And if I need it, the conjugate of that, I just change the sign of the imaginary piece, or I could just change the sign of j, and now it's minus j. This was purely imaginary. And so all I have to do is introduce a minus sign in the entire expression to change or to conjugate the impedance. The reason I did that is, what's the formula for the complex power of a capacitor? S sub C. In generic terms, it's the voltage of the capacitor times the current conjugate, right? That hasn't changed. That's still our same expression. But what I want to do now is replace this current by a ratio of voltage and impedance. So that's just the generalized form of Ohm's law, V over Z. And this gives me or, in terms of what I've just written down, and the reason why I kept the minus sign downstairs is now I can multiply both top and bottom by minus j omega c and get rid of that ugly fraction in the denominator. And that's now my expression for my capacitor's complex power. That's now my minus j omega c v squared. This is what I want to use to get rid of plus j 57k. My original load of load 1 and load 2 was inductive in nature, and it looked like j 57k. Now I need to pick, the only thing that I have left to pick is C. What's V? That capacitor was still across the same voltage polarities, wasn't it? Or the two terminals, and that was 500. We know what that was. That's 500. The only unknown is C. We want S sub C to equal minus J 57K. They're just dying to get in here. Or we now have minus J 57K is equal to minus J omega C V squared. The minus J's cancel, and I can solve for C. C is now 57K over omega V squared. And what's omega? We had a Hertz expression of 60. 2 pi 60 is 377. Or we now have 377 and 500 squared, or C, becomes 605 microfarads. We hang that across our load, or loads, and we will have corrected our power factor to be equal to 1. and we'll pick up at that point on Tuesday. Please make sure your homework, if you want to turn it in, is turned in here. Put your in-class participation on the leftmost table, and you have until 4 to turn in your homework. You can put it in my mailbox over in the ECE building. Have a good weekend, and I'll see you on Tuesday.